Go back and sender's finite state machine. Before we start talking about this, let me review RDT 3.0 sender's finite state machine. And here it is, the RDT 3.0 sender. Okay, so we're starting here. Okay, and there are 4 typical transitions: 1, 2, 3, and 4. So first is to get a call from above. We generate the packet starting from packet 0, send it out, and then start the timer. The other is getting a feedback from the receiver. If it's not corrupted and it is indeed the egg we're expecting, then that's a positive acknowledgement, so we stop timer and move on to send the next packet. Third is when it's a little bit unfortunate, the packet is not correct or not arriving at the receiver, timeout will be triggered. So we retransmit the packet and start the timer again. Last one is when you get the feedback, it's unfortunately corrupted, then we do nothing. So we kind of ignore these 2 conditions on purpose. The second condition is, yeah, we get an egg all right, but this is what? Carrying 1, which indicates this is a negative acknowledgement. Right? So in these 2 cases, instead of quickly retransmit, we just ignore. Right? So this is a quick refresh of RDT 3.0. In Go Back and Sender finite state machine, we also have these 4 transitions: getting a call from above, receiving feedback from the receiver and it's not corrupted, having the timeout event, as well as getting feedback from the receiver but it's corrupted. Okay, very similar. And then we go through them one by one. Now let's start from the getting a call from above transition here. Comparing to RDT 3.0's getting call from above transition, this one is pretty long. Yeah. And it starts from a if-else condition check. And the condition is this guy here. If the next seek num is less than base plus n, so base plus n is what? The window range, isn't it? If the next seek num is within the range, that means, okay, we can now generate still some data packets. So, makes sense. We go ahead and create the packet using the data from the application layer, generate the checksum for the data, and then give you the sequence number. Okay. Here. We are now using an array of send packet here to store all the packets being generated. This is because Go Backend is a pipelined RDT, meaning there will be multiple packets in flight, so they will be generated, being transmitted, but not yet acknowledged. So these send packets will need to be stored temporarily at the sender before they are acknowledged, because chances is high that you need to retransmit it somewhere later. Okay, so we need an array instead of just 1 packet there to store the packets that are in flight. Next step, send the packet out. And then we need to start the timer, right? This is to handle the cases we could have packet losses. Just like in RDT 3.0, the difference to RDT 2.something is to have these timers. So we need to start timer, definitely. But in Go Backend, we have 1 timer for the entire flight of n-act packets. So we need to check, right? We cannot be starting a timer for every data sent. So here we're checking. If the packet we are now generating is indeed the base, the first yellow packet, because the timer in Go Backend is associated with the first yellow packet. So associated with the base. So only when the packet we are generating is the base, then start timer. Otherwise, don't. So this ensures that we have only 1 timer for 1 flight of n-act packets. And the last is straightforward, just increment the sequence number by 1. Right? So this is if the next seek num is within the window. Otherwise, refuse data. So this is telling the application layer process saying that, hey, I cannot be sending more data packets. So you hold on and you try calling the RDT send after some time. And the second one that we'll examine is this guy here. All right, so this is supposed to be the case where we receive acknowledgement, and it's a new one, therefore we could what? Move on. All right, so let's take a closer look at how the move on is like in go back and sender. First of all, the checking condition. Yeah, get a feedback packet coming from the receiver from the lower layer. And if it's not corrupted, oh, good. So the feedback packet is not corrupted. So this must be one of those what? Cumulative ACKs. So inside the ACK, there's going to be carrying a sequence number. So why don't we get that sequence number out? So get ACK num. Okay, so this is a new function call introduced into go back and's finite state machine. So that is just, a bit abstract, but what it does is to get the sequence number in the cumulative ACK packet here. All right. And we simply change the base to that sequence number plus 1. All right. So this is the first packet that is unacked. Hey, makes sense, right? Receiver sends a cumulative ACK. So that ACK carries the sequence number n, which indicates all the sequence numbers before that, including n, are acknowledged. And the n plus 1 is the first in the gap in the receiver. The first one, that ACK cannot be acting. Okay, therefore, base is assigned to that value. Okay, makes sense. Oh, but we check. So just like in the generating data part, there are a lot more check. Being careful here. If the base is nulled, the next seek num. What does that mean? Base should be the first yellow, and next seek num should be the next data that is allowed to send. But next seek num cannot be a yellow packet, right? So if they are the same, that means there are no yellow packet at all in the window. Okay, which means all the packets that's not yet act at this point in time are already act. Okay, so stop timer because there's no pending packet waiting for acknowledgement. Otherwise, restart timer. So we receive a cumulative ACK. The base is reassigned such that it's pointing to the first yellow packet. Okay? And so we refresh the timer for the first yellow packet for the base. Okay? So restart timer. All right? So the only thing that's a bit odd is this. There's an if condition to check whether we should stop the timer because all standing packets are cleared. All yellow ones suddenly turn green. Or we need to refresh because the base is either refreshed or changed to a new value. And therefore we need to restart the timer for the refreshed first yellow packet. And the third transition is straightforward. It's actually very similar to RDT 3.0's timeout event. We restart the timer and retransmit the packets. In RDT 3.0 sender, we retransmit only one packet, but this time in go back in, we retransmit for the entire flight of packets, starting from the base to the packet right before next seek num. And the fourth transition is this: when the sender receives a feedback, and it's a corrupted feedback, then we do nothing. So this is just like in RDT 3.0, when the sender receives a corrupted ACK or a duplicate ACK, which is a negative ACK, it does nothing. Okay. Now the difference here though is that it only handles the corrupted ACK case. What happened to the duplicate ACK? In go back and sender, it's actually handled here. when the sender receives an ACK, it's not corrupted. Whether it's a new ACK or a duplicate ACK, the actions are the same. If it's a new ACK, the base will shift to the right. But if it's a duplicate ACK, if it's a duplicate cumulative ACK, the base will remain the same. Right? Would this be a problem? Now, some of you might not be very comfortable with this, right? Because, hey, if the base remain the same, what do we do here? Yeah, we'll be definitely in this situation, right? Yeah, there's an unact packet somewhere and the base remain the same. We'll be restarting the timer, meaning the first time that base is receiving an ACK for all the packets before the base, the timer for that base has already been started. And now we're reassigning the base to the same value and restart the timer. That means we're extending the timer interval for that base. How do you like that? Think about it. And the last bit of the go backend sender, or shall I say the first bit of the go backend sender that we actually talked last, is the initialization of the sender. Okay, so the base, starting of the window, is initialized to sequence number 1. Next seek num is also initialized to sequence number 1. So this is unlike the RDT 3.0 sender receiver, always starting from packet sequence number 0. In go backend sender, textbook authors decide suddenly that they want to start from the sequence number 1. Now, the receiver finite state machine of go backend. It's actually quite simple. Let's just skip the initialization and focus on the 2 transitions possible. Among the 2, this one is the more straightforward. We receive a data, get a call from below, and check the data, it's not corrupted, and check the sequence number of the data. Has seek num there is a function newly defined for go backend again. So what it does is simply checking the sequence number in the data and see if it matches the expected sequence number, which starts from sequence number 1. So if we receive packet 1 and it's expected, extract data out of packet 1, pass the data up to the application layer, generate ACK packet for packet sequence number 1, send the ACK out, increment the expected sequence number. Okay, so this is the simple case where everything works as expected. No error, no loss. And the second case is the default transition. What default meant is just all the other conditions that's not matching the previous transitions condition, which means the data can be corrupted or the data received not corrupted but not carrying the sequence number expected. So here, corrupted data or data packet that's not in the expected sequence number. Now this could be a duplicate data packet. This could also be a data packet carrying the future sequence number. So in either case, which means default is just to send the same packet again. That is the packet generated here, which is the ACK packet that is generated previously when data arriving correctly and in sequence. So in case of corrupted data, out of order data, we discard the data, no receiver buffering, so there's no extract of data, no passing of the data up to the application layer, and all we do is simply react to the data with the highest sequence number arriving correctly in order. So go backend receiver there works a bit odd, not that intuitive, but it's very simple. It always acknowledges to the data packet that is the highest in sequence number for all those who arrive correctly and in order. So all the receiver needs to track is the expected sequence number. And that's pretty much all. At the sender side, if a duplicate ACK is received, that is essentially saying either the data previously sent is corrupted or the data previously sent is lost.